So in an earlier video, we looked at the step response of an RC circuit. In the language of electrical engineering, that's a time domain approach to asking, if you put a particular function of time on this circuit, what's the response as a function of time? Now we want to think about it in a slightly different way that's very related, but also very useful. So I'm just going to draw a capacitor here. It works beautifully to think about it in an RC circuit, but we can get most of what we need starting just with the capacitor. And since I'm interested in IV relationships, I'm going to put a current across it, and I put that too close because I want to make sure that we label these all now as functions of time. And we'll say that it's got a voltage across it, and I'll put a VC there to remind us this isn't a resistor. So now let's imagine that the voltage on the capacitor, we'll just put this on with a function generator, let's say. Maybe that function generator will have a voltage amplitude of V0, and it'll be a sine wave with a radian frequency of omega. So that seems like a pretty good function. It's a favorite. Let's figure out what the current is. I of t equals C dV dt. So let's see. Let's keep the capacitance. We probably need, I'm going to take the derivative. So if I take the derivative of sine omega t, I'm going to get omega coming out, cosine omega t, since the derivative of sine is omega cosine. Oh, and I've still got the amplitude of that sine wave. So my driving function is a sine, S-I-N, and my current responds with a cosine. Again, very different than a resistor. If you put a sine wave across a resistor in the voltage, the current will be a sine wave. It's instantaneously the same. But with this device that has this derivative relationship, they're always 90 degrees out of phase, and that's a dramatic difference. The thing I want to emphasize, and what's going to be really important here, is that omega that came out. That does something super important. And to try to understand that, we actually need a concept that we don't quite have all the math yet for, but we'd like to calculate something which is sort of like the resistance of this capacitor. It doesn't formally have a resistance. It's got Ohm's law is about resistors. But it's got some character in that there's an amplitude of this sine wave and an amplitude of this cosine, that's the current, and the ratio of those might have a character like resistance. And it turns out it does. It's a concept called impedance, but it can keep track of the fact that these functions are different. We don't have all the math to write that down, but I can write it down in a way that is formally correct, and we can talk about it. So Z is the symbol for impedance, and the bars around it mean absolute magnitude, because it turns out that's a complex number. We don't need to know that. We just need to think about this as this sort of like resistance quantity. So I'll write in quotes here that this is the resistance of the capacitor. And it's a similar concept, and it'll be enough for us to understand something important. And what it'll mean here, let's see, if you remember V equals IR, so resistance is like voltage over current. What this will mean will be the maximum of V of t, C of t, over this maximum, or the amplitude formally, of I of t. So these terms out front. And that'll be this concept like resistance. So let's write that down. So the voltage is swinging back and forth with a sinusoidal amplitude of V0, and the current responds with capacitance, omega, and V0, which of course those cancel out, and we get 1 over C omega. And that's an important thing. First of all, this has units of resistance. That's kind of cool. That's got units of ohms. And it's frequency dependent. And that is the super important thing. Why is that? Well, let's now go back to our favorite circuit with two elements in it, which is something in series. And let me put some V source of time up here. Here's a resistor, here's a capacitor. And let's think about this now as a voltage divider. The voltage at this spot here, which would be VC, because this is 0 volts, it would be, if this was a resistor, the voltage here would be this resistance over the sum of the resistances. We can't quite directly add these because this being a complex number again, but we can see the character. If my source, this could be some signal I want to process, if it is varying quite slowly, and by slowly, I mean relative to the RC time constant, then I put this source on. It's sort of constant for a long time. It's varying slowly. And what would happen is the capacitor would charge up, and it would charge up to be about the source voltage, because this system can respond faster than my signal is varying. This is slow. This system responds quickly. So my capacitor always charges up, and in that case, VC equals V source. So it would just pass through. There'd be almost no current all the time. That's for the case at very low frequency. Well, let's see if that's consistent with a voltage divider. If the frequency is very low, then this number is very small. Then this resistance, this impedance of my capacitor is very high. And if this were a voltage divider, if this was much higher resistance than the top one, I would indeed expect all the voltage to drop across this second element. So that sort of sounds consistent with how this should operate. Conversely, what if I went to very high frequency? Then this number would be very high, and the resistance of my capacitor would be very low. That would make this effective resistance much smaller than R, and I would expect, if this was a voltage divider, that most of the voltage would drop across the resistor, because this one's now smaller, and in that case, I would get essentially 0 voltage across the capacitor. So now let's think about how this circuit would respond to changing this frequency. We see that it should respond differently to changing that frequency because the resistance, in quotes, of this element here depends on frequency. So we've made a frequency-dependent voltage divider. And as this resistance, again in air quotes, changes, we'd expect the voltage division ratio to change, and then we'd get different voltages at the intermediate point as a function of frequency. So let's take a look and see what that would look like. The voltage across the capacitor, if we're at 0 frequency, at 0 frequency, a capacitor is an open circuit. It's 2 metal plates, and you can't shove anything across it. We see that here because if we put in 0, its resistance appears to be infinite. That's what an open circuit should be. If we have an open circuit, there's no current. If there's no current, there's no voltage drop across the resistor. All the voltage is across the capacitor. And we'd start with V0 here. We would just get a voltage here that would be equal to, in amplitude, the size of the source voltage. At very, very large frequency, now we slosh electrons back across this gap and they're pushing each other back and forth. The frequency is infinite, the resistance goes to 0. Capacitors are short circuits at infinite frequency. Well, if this is a short circuit, we shoot 0 voltage across it. So at very, very high frequency, we get 0 voltage. And therefore, in between, we get some function which connects them. This is a low-pass filter. If we drive various frequencies omega into this device and sense at this intermediate point, we find that for low frequencies, we get a pretty good copy of the amplitude of the source out, but as frequencies go higher and higher, it's attenuated off. So if this was an audio system, my voice might fit down here, but if there was a soprano singing with me, she would be attenuated and you would hear her less. This would be a good way to make a bass knob on your stereo system to pass the low frequencies or amplify them, and you'd want the other behavior, a high-pass frequency filter, if you were trying to pass the trebles.